Okay, so I didn't hear this, but I guess we have started recording. So, okay, so last time what we did was we are going towards tensor products. Okay, so towards tensor products, and so last time we saw some of the preparatory material. So one was the third was the free vector space. The second was, I think the first was the first was quotient spaces or quotient vector spaces. The second was bilinear maps. And in fact, we saw that if you look at the dimension of the F dimension of the bilinear maps from V cross W to F, and V and W are finite dimensional, then this dimension does equal the product of the dimensions. Except for the fact that this is a space of bilinear maps, not linear maps. This is indeed the case. Okay? So this is indeed a vector space whose dimension is indeed that of the product. But what we want is to say somehow that we don't want some space of maps, we want the vector space itself. Anyway, for now we also saw this thing, which I'll just repeat that, as I said last time. The free vector space on any set D is literally, if you want, so what you can do is you fix a set VD. I'm not saying that these are occurring somewhere. I'm just fixing these sets, which I will specifically call as vectors, indexed by D. And then now after this, you define this to be the set of all finite linear combinations, and say alpha D VD, where alpha D belongs to the scalars. And this is finite linear combinations. Okay, and then it's clear that the sum of two such expressions is still a finite linear combination, and the scalar multiple is the same, and this is a vector space. Okay, and the point is the basis of such a vector space is precisely V. This is the basis. So these are the three ingredients we saw, and with these ingredients at hand, we can now actually write down the theorem about tensor products. So I think that's straight away what we do. Yeah, let's start. So maybe I'll just use a new pen for a change. So theorem. Okay, so given so let's say given vector spaces, V and W over F. Let's see if this is readable. Yeah, it is. Yeah, given vector spaces V and W over F, there exists a vector space, comma, there exists a vector space V tens, which I will call as V tensor W over F again, with the following property. Okay. And a map, and a bilinear map from and a F bilinear map, let's say. Pi from V cross W to V tensor W, satisfying the following property. And what is the property? The property basically says look at all maps that go from look at all possibilities when you have a bilinear map going from V cross W to Z. On the other hand, I know that I have a bilinear map pi going from V cross W to let's do this other one named P. Yeah, pi from V cross W to V tensor W. Well, whenever I have, so basically in some sense I'm saying look at the category of vector spaces Z together with a bilinear map V cross W to Z. I'm looking at such objects. Well, this one is one such object where Z equals V cross B tensor W. I'm saying whenever you have any other object like this, there exists a unique map making this commute. And so I'll call this T tilde. There exists a unique, and this map is not bilinear, this map is linear. Okay, so that's what I will say, satisfying the following property. So given a vector space Z over F and a bilinear map, T from V cross W to Z, there exists a unique linear map T tilde from V tensor W to Z such that T tilde such that what? Well, you know, such that this diagram commutes, meaning T, you can either act by T and directly go to Z, or you can first act by pi and then by T tilde, and you get the same answer. Okay, so what we are going to do, is we are going to take the what do you call it? We are going to first prove first I'm going to tell you what the space is. Then we will prove that it has these properties. Okay, so maybe you can start the proof here itself. So step one is to construct. Maybe at least for the steps I should use for the headings I should use the blue pen. Here we go. Proof. So step one, constructing V tensor W. Okay. So what we do is now we are going to define some very big space. The idea is we are going to combine all these ingredients. So we are going to start by defining a very big space with the entire set V cross W as a basis. This set is V cross W. So it's like saying, think of the real line. The real line is a vector space of dimension 1. Instead, now think of the free vector space over the real line, where every real number corresponds to a basis element. Like V1, V2, V minus 1, V pi, V square root 2, VE, all that. So uncountably many basis elements. So it's like a very big space. The same way, V cross W is itself a vector space. We are going to take the vector space with basis V cross W. Okay? And then what we are going to do is we will quotient this vector space by a subspace. And so I'm going to use, first of all, to construct, I will use property this construction 3 and construction 1. And of course, the property that it satisfies involves construction 2, which is bilinear maps. Okay? So start with this one. So I'm going to, instead of saying V and W, because I already have V and W, I will use A and B. So like a vector space free is going to be something like A, and quotient is going to be by a subspace B. Okay, so define A to be the free vector space over V cross W. Okay, and now let me define B. So this is just, you already saw this. Let's give a basis. I need to index, so fix a basis. And I will use some kind of pictorial notation with basis. I will draw them in rectangles, V comma W. Okay. V comma W, where V is in V and W is in W. So 0 comma 0 is also a basis element. 0 comma 0 inside a box, such that V is in V and W is in W. So I will use this basis all along. And now define, now consider the span of a certain subset of vectors. Okay. Now define V. And define B. To be the span of the following set. So first of all, I want to say something like bilinearity. So I want to say V plus V prime comma W minus V comma W minus v prime comma w. Okay. Similarly, v and w plus w prime minus v comma w minus v comma w prime. And similarly, and I want to do c times v comma w minus c times v comma w. Remember that this is a vector space, so it's a vector space over F, which means that I can take scalar multiples of this basis element, and that's what I'm doing. C times v comma w, and the other one as well. So v comma cw minus c times v comma w again. The span of all these elements, they're running over all v prime in D, w prime in F, and C in, oops, this is W first of all, F, C in F. Okay, so this is, since it's a span of a certain set of elements, therefore it's a subspace. So B is a subspace of A. It's not just a subset, but a subspace. Finally, we can define V tensor W. Define V tensor W literally as the quotient module A mod B. That's all. So that is the definition of the tensor product. It's an enormous space divided by another reasonably big space. Okay, great. So now that is part one. This is the construction. Okay. Oh, I need to also define pi. Okay, well, define this thing and pi of V tensor W. Sorry, pi of V comma W. To be what? Well, remember, this is, so I'm going to say it is equal to VW, of course, except for the fact that this element does not sit inside the quotient space. This sits inside A. What is A over B? It is a set of equivalence classes of elements of A under some relation, where two elements are equivalent if they differ, if the difference lies in B. So I just say it is the equivalence class of this. This is an A over B. Okay, so now we have the full definition of that we need. This is step one. Just to construct, just to define what is the tensor product and the thing. Okay, so yes. So now we come to step two. Maybe I should write that in a pen. Oh, I should have said one more thing. This is, I'll erase this, of course. I'm going to give this a name. Eventually, we will give this a name or definition. This is exactly what we say as V tensor W of vectors. Okay, fine. So now let's write down the proof. So okay, the first claim is step two, pi is bilinear. Right? We have to say that this is a bilinear map. So there exists a vector space and a bilinear map, and then we show the property. So pi is bilinear. So how do you show pi is bilinear? This is also very standard. So all you do is just start verifying. So let's say I want to look at pi of v plus v prime comma w. So let's start pi of v plus v prime comma w. So first of all, what is it? It is the equivalence class of v plus v prime comma w. But now, because of this, since you are quotienting by this relation, right? This minus this much lies in w, lies in b. You are quotienting by b. So therefore, this is equivalent to this plus this, right? So I could say this and this like this. So this expression is equivalent to the sum of those two because the difference lies in b. B is the span of these things. So this equivalence class is indeed equal to v comma w plus v prime comma w. And then what we know is by the definition of the quotient space, this is the same as saying it's the equivalence class of this plus the equivalence class of this. That was the definition. Right? So this is equal to VW equivalence class plus V prime W equivalence class. But what was VW? By definition, this was pi of VW. So this is pi of VW. And similarly, what was V prime W? Equivalence class. This was exactly pi of V prime W. So indeed, pi is linear in the first coordinate and similarly in the second coordinate. Sorry, I should have said C as well here, right? So if you want to check linearity, you have to multiply by a scalar. Sorry. I have to add a C everywhere, but that doesn't take too much trouble, too much effort. So first of all, again, I can put a C here slowly. Let's go slow. Okay. At some point, I'll skip a step. So maybe this is the place to skip a step. You can check again by the definitions that this is exactly the equivalence class of V comma W. And the class can be multiplied by C. These are all definitions. How to multiply an equivalence class by a constant, how to add two equivalence classes. Where this is exactly equal to C times pi beta. Okay, and similarly pi is linear in the second component. This is part 2. Pi is indeed bilinear. Now we come to part 3, which is the property. Second. Yeah. Okay. Where should I this here? Part 3. The universal satisfying. I don't know if I said universal property, but I'll just say it here. Okay, 1 second. Okay. Now, how do you show this? So let's see. So we have to define it, right? So let's see. Given all these things, let me keep the picture just in case it's useful. There exists a linear map from this. So given T as above, so given T as in the theorem, define T tilde of, okay, so now I have to define it on V tensor W, right? So, okay. Let me see. How do we define it? You have to define it. Okay, I'll start using this notation. So remember that these guys, the VW form, this collection of these vectors form a basis of A. So every element of A is a finite linear combination of such things. And so indeed of the quotient space is still a finite linear combination of these equivalence classes. Right? So therefore I will start saying with Ci Vi tensor Wi. Let's say I have this thing. Define this to be what should you do? Well, you want the answer to be exactly the same thing, right? So basically you just have to say something like this. There's only one possible choice. Ci T of Vi comma Wi. Let's say, since normally I'm used to summing up from I goes from 1 to n, so I'll say 1 to n. But I think that's exactly what you have to do. Check here. Yeah. Sure, I wrote VIWJ, I don't know why. Oh, sorry. So I need to do this, but I need to do this in 2 steps. So first of all, let's do this carefully. I want to prove there is a universal map, right? So, but let's do it in 2 steps. First of all, let me define. So T goes from V cross W to Z and is bilinear. So first of all, I define T1 from A to Z, from free of V cross W. And then I will define it, then I will say something about A over B. A equals free. So now, remember again, so in A, the VW followed exists. So I write down exactly that. So T1 of summation Ci Vi comma Wi. I goes from 1 to n to be summation Ci, and then T, indeed T itself of Vi comma W. So exactly the same definition, but I'm just saying that I will first define it on A. Okay? Now what happens? You can check that this is indeed, now A you see is the vector space, right? It is not 2 vector spaces. So you can check that this map is linear. Because T is bilinear, this map is indeed linear. Okay, let's see. Actually, I refuse to. Should I? Let's see. Let's do this. So suppose I have this is linear from A to W, A to Z. Since if I take T1 of some summation Ci Vi Wi plus alpha times di. So the point is this, it's a finite sum here, it's a different finite sum here. I take a union of all these basis vectors that occur in either sum. And I just add the 0 times that if that basis vector doesn't occur in this sum, 0 times whatever doesn't occur in this sum. So therefore I can keep the same set of VIWI. I goes from 1 to n. Okay? And now what do I do? Well, this is exactly equal. This is equal to what? On the one hand, so first of all, this is equal to Ci plus alpha di, right? So it is summation Ci plus alpha di T of Vi Wi. So on the one hand, it is equal to this. On the other hand, sorry. But now what is this? This I can rewrite into, I can break this up into 2 summations, right? So it is Ci T of Vi Wi plus alpha times summation di T of Vi comma Wi. But now what is this summation Ci Ti Vi Wi? This is exactly T1 of this thing plus alpha T1 of this thing. And so indeed it's linear. So usually this is what happens. Verifying linearity is a trivial exercise. It just involves understanding the notation in the problem. But then it's exactly the same as any other question where you verify linearity. Anyway, so the point is this is a linear map. So given a map, a bilinear map P, I've just verified it's a linear map. And there was really, I don't think we made use of the bilinearity in any case. We just wrote it out completely formally. Okay, fine, this is linear. Now, moreover, now remember I quotiented by these relations. Then what happens to T1 of B? The claim is that T1 of B is 0. Remember what B was? B was a subspace of A. The claim is that T1 sends B to 0, the 0 vector in C. Indeed, let's verify T1 of what was one of the bases? B plus B prime comma W minus v comma w minus v prime comma w. Okay, so what is this? Because we verified it's linear, I can just take everything linearly. So I get that this is equal to T1 of, maybe I'll write that step down and not jump steps. But basically, you know, T1 of this term minus T1 of this term minus T1 of this term. Because of linearity. And you know what to put in here. But now, what is T1 of v plus v prime comma w? It is summation C1, so it is this thing, right? So this is equal to T of v plus v prime comma w. So far in the linear part, I have not checked, I have not used the fact that T was bilinear. Now we will actually use minus T of vw minus T of v prime w. But now what is this? This is T is linear in the first coordinate. So this is exactly equal to this plus this. And so this is exactly equal to 0. Similarly for the other three types of vectors. For the other vectors spanning the set. V was the span of a certain set of vectors 4 times. Well, for all of the other vectors spanning V. Spanning V. All of this since all this holds since T is bilinear. So all this holds because T is bilinear, so all these relations become 0. So now what do we have? We have a linear map from A to Z which takes B to 0. And this is where you have to remember homework, whatever, I think 6 or 5. The quotient, the universal property of the quotient module is whenever you have a linear map from A to Z, taking B to 0, it factors through a linear map from A over B, A quotiented B to Z. So by the universal property implies property of quotients, of quotient spaces, that is. There exists a unique linear map, and that uniqueness is exactly what we want. Of A over B. But what is A over B? That is precisely V tensor W. To Z, as in the picture that I raised, there exists a unique T in T tilde linear thing, such that what? Such that the equivalence class, such that T tilde of the equivalence class of V comma W equals exactly T1 of V comma W. But what was T1 of V comma W? It was exactly T of V. And that is exactly what we wanted. T of VW is T tilde of the equivalence class of V comma W. Because this is the same as I defined pi already, so this is exactly T tilde of pi of V comma W. So there exists a unique linear map sending exactly this vector via T tilde, first pi and then T tilde, or via T itself. Okay. So that I think is the end of the proof. Okay, great. So yeah, this was homework 6. Okay, great. So that's that. So now, okay, that is something about tensor products. So that was step 3, universal property, and then we are done. So that's how we construct a tensor product. And now for the, remember the original goal of all of this was that, the product, the direct product or the direct sum of vector spaces, the dimension of that is indeed the sum of the dimensions. And we want to say that there exists something like the product for which the product is, there exists something whose dimension is the product of the dimensions. Well, now this is what we are going to see next. That's the next theorem. If, let's say, and this is not just true for finite dimensional vector spaces, but for infinite dimensional ones as well. So if V W over F have bases Vj, let's say, and Wi, then V tensor W has basis Vj tensor Wi. So indeed, so in particular, if the dimension of V is n and the dimension of W is m, then you indeed get the dimension of V tensor W. At least when both are finite. When these dimensions are finite, then this is a product of two numbers and it equals some number, which is the dimension of V tensor W. Okay, so you have to prove both things. This is slightly subtle, but this is kind of more in the flavor of algebra 1 in some sense, the proof. Well, half of the proof. But that's the point. I want to show you in this course already what is the power of this universal property. So the point is, you have indeed used, we have explicitly constructed the vector space A tensor V as so V tensor W as A quotient by V, where A is some big space, V is some small space. But beyond the construction, and I think I said this once, is construction is great to prove existence, but beyond that, the uniqueness part follows from the universal property. There is only one construction up to isomorphism in that category which satisfies the universal property. So in a sense, the universal property captures the entire object, if it exists. So beyond constructing it, everything else is captured by the universal property. So in every single proof, you might as well just use the universal property. And that is what we will do here in some sense, at least to prove linear independence of that set. Okay, so proof. So I don't need to tell you why the corollary is true, right? Because if this set has size m and this set has size n, then this set has size m times n. That's all. So proof of theorem. Okay. So let's first do spanning set. That is the easier one. That this set, let's call this, let's give this a name. B. So B spans V tensor W. Why is this true? Well, this is true for the following reason. Actually, this is just pretty much standard, right? What can I say? Take any, I mean, write down any vector space. So, what should I say? Okay. Let's do, look, let's write it down in full notation. So, every element not of V tensor W. Remember, this is A over V, right? So it is the set of equivalence classes of A. So it's enough to show you that every equivalence class of A is a linear combination of equivalence classes of these things. Right? So yeah, so every element of, let's say, A itself is of the form summation C, Ij, Rs, what do I say? C, Rs, PR, Qs. It's a finite sum, of course. But here where PR is in V and Qs, sorry, oops, is in W. Which means now PR can be written in terms of this basis and Qs in terms of that basis. So say, I'm not saying the bases are finite, okay? This can be infinite basis. So say PR equals summation. This is in V. So let's say J in J. C, pen, C R J Vj, and Qs equals summation I in I D. Oh no, I think I want this to be D. I normally put DJ Vj, and this is C. C S I W I. Suppose this is true. Okay. Then, because of the equivalence class relations, but let's write this out. Yeah, fine. So a general element of, you say spanning set, right? Actually, I want to say every element of this set belongs to something like that. Is a linear combination of these. And every element of the Tensor product is a linear, is exactly the equivalence class of such an element, of elements of E. Okay? So now, or let's not say since every element, since V tensor W consists of elements of the form A, where A is an A. And this is A, so this is like A. Okay, so this is my A, and V tensor W literally consists of, it is A, this is capital A over capital B. So it consists of equivalence classes of elements in A. That's what I'm saying here. Okay, since we now compute we are done by computing. So we compute, let's compute this equivalence class of A. Equivalence class of A. Again, by the quotient vector space properties, this is summation R and S. Of course, it's a finite sum. C R S P R comma QS. But now PR and QS are like this. So again, you can still do more linearity. CRS, and you can also add I and J. Okay, and now you write down this. You write CRS. Now you want D. Oops, SJ. Something is very wrong. DRJ, sorry. Something is there. These should be, the J should be below, and the R should be above, and here the S should be below, and I should be above. Something is very wrong again. No, that's good, that's good. I should be below. So CRJ, CRS, DRJ, and W, sorry, not W, CSI, and then the equivalence class of VJ, WI. That's what this is. You literally expand it out and you get this. But now, because all of this sum is finite, because the sum is finite, I can exchange the order of summation. And so I sum over I and J, and what I get is the following. So I in I, J in J, and now, first let's sum up all these scalars. So C, R, oh, I can't write this stuff. How do I write this? I write it upstairs and in blue. So C R S B R J C S I, whatever this scalar is. So this is being summed over R and S, and then yes, you can even call this like alpha ij or alpha ji if you want, either way. And now we write down here. Sorry, and these are equivalence classes. So Therefore, this I should be putting brackets around them all. Vj Wi. So this is literally equal to, but what is the equivalence class of Vj Wi? This is exactly Vj tensor Wi. That. This is equal to Ij alpha j alpha ij Vj tensor Wi. And that's what we wanted to prove. We wanted to prove it's a spanning set. Well, here any element is a linear combination like this. Where alpha ij is this finite scale. Okay, so that is one. The second is that B is linearly independent. That is the tricky one. So for that, as I said, you have to use the linear, the universal property. Sorry, where did my notes go? Okay, so then after that. Okay, so first of all, let's define the following. So first I will define a map that I will claim is bilinear from V cross W to F. Okay, so F, not to Z, but to F. Define. So maybe given first of all. So given an I and J, or let's say I naught and J naught. Given J naught in J and I naught in I. Define the map phi J naught comma I naught from V cross W to F. So this is my Z, which is F via phi J naught I naught of V. Let's see. So everything here is a sum of is a combination of the VJs, DJ, BJ, and summation J in J, finite sum, and I in I, finite sum, C I V I W I. And literally all it does is it picks out the J naught and I naught coordinates. So it's D J naught and C I naught. Define this map. Okay, once again you can check, and I won't do it this time. I did one of those checks earlier in the proof. Check that this is linear, but this is bilinear. And this is what I'm calling Z. This is what I will be equating to Z. And now I have a bilinear map from V cross W to Z. So I can apply my universal property again. So this is the idea, is you keep applying the universal property of the tensor product. So, this is the linear independence part, this is where I apply it. And so the question is V tensor W has that basis, right? So I'll not erase it because then I will eventually erase the whole thing. So because of there is a bilinear map, so by the universal property, there exists a linear map, unique in fact. Let's call this, I will call this of course phi tilde J naught I naught from V tensor W to F such that S dot T dot is such that, as we know what it is, right? So that phi J naught I naught equals phi tilde J naught I naught composed with pi. But now I'm going to apply this on both sides. Okay, so first of all, these maps exist. Fine. This is part A. The existence of these maps is now they're ready for us to use. So now let's start to prove the linear independence. Suppose this set B has a dependence. So now for the proof, now to the proof. Now for the proof. Suppose there is a linear relation which is summation Cij Vj tensor Wi equals 0 in the V tensor W vector space, in the vector space of which is the tensor. And again, you sum a finite sum, but over I in I and J in J. Suppose this is true. then I can apply phi j naught. I can apply phi j naught tilde I naught tilde. Right? So, but what is this thing? This is equal to pi of summation Cij Vj comma Wi. Right? That's exactly what is the pi of. So applying phi tilde, we get that phi tilde of pi of this expression equals phi tilde of phi tilde means phi tilde j naught I naught. So phi tilde j naught I naught of is not phi tilde. It is, but the point is this expression is 0. Pi of this thing is 0. This is 0. So phi tilde is just phi tilde of 0, which is of course 0, which is the 0 scalar. Right? Phi tilde takes values in the field. On the other hand, phi tilde composed with pi is exactly phi. So we exactly get phi of that. Phi of the expression without the pi. See, phi j naught I naught. So say phi better. I comma j. Cij Vj Wi equals 0. Okay, but now you see here I can do the following. This here exactly I know what to do. It is exactly equal to C I naught j naught. By the definition of pi, we get C I naught j naught equals 0. And I'm doing this for every single I naught and every single j naught, and therefore I get for all I naught. And that proves linear independence, and hence it's a basis. So that's all. So this is just a matter of, all of this is just a matter of decoding notations from, tuples like pairs like this to the equivalence class, which is just a tuple, which is just a tensor notation, and then so on. But it's nothing, the math is, the proofs are very short. It's just the fact that you use the universal property. Once you have proved it, it's available for use. Okay, great, so that's that. And so as I said, the corollary was that if you have a vector space of dimension m and a vector space of dimension n, then their tensor product has dimension exactly m. Whereas the direct sum has dimension m plus n. And somehow that's why the notations are also v plus w with a circle, the dimensions add up. And v tensor w with a circle, v cross w, the dimensions multiply. So I don't know if the notation was done after the universal property, or at least the dimensions were computed, but that's the notation we are stuck with, which is very nice. Okay, so this basically already, so here is where maybe I should say this marks the end of category theory, all the category theory stuff that I said. So this is the end of that. End of category theoretic part. We will still do other constructions, like I told you about the sum, the intersection of a bunch of subspaces and the sum of the bunch of subspaces. Those were not category theory; those were vector spaces. Right? So, but so they did not involve any universal properties, for example, and so on. So we will still do some more constructions like that. In fact, starting right now, we will talk about the dual vector space. But it is not category theoretic. I'm not going to give you some universal property that the dual space satisfies. But we will of course define, study, and so on. The dual spaces as well. See examples of dual spaces are important, and we'll see one construction that already shows up over here. So let's see. So Okay, let's start doing stuff slightly faster now. Where is the okay, the category theory is over. So, okay, great. So now let's go slightly faster, as I said. Okay, so now we come to dual spaces. We have seen bilinear maps and so on, right? So we have seen bilinear maps from V cross W to F, which I wrote at the very beginning. As is defined the dual space. The dual space of a vector space is, we call it V star. The definition is it's literally the set of linear maps, F linear maps from V to the ground field. That is the dual space. Now, obviously, because we already proved that the set of linear maps from any vector space to any other vector space is itself a vector space, so clearly this is a vector space. First of all, I'll say that. Before that, I will say elements of V star are called linear functionals. So not functions, but functionals. AL. Okay, and now of course remark it's a vector space. Okay, I'll say that as a lemma apparently. So fine, let's write down the lemma. So basic properties. One is of course V star is a vector space. But you can say a little bit more. Sorry, and of course maybe I should say the zero map. The zero linear transformation is exactly the zero in the dual space, in V star. Yet secondly, if you let's look at the dimension. I wrote the dimension. Oh, that's much later. Why is it that later? Anyway, fine. We'll do that later. Okay, so first of all, let's look at the only other part here is the dual space of F to the N. These are column vectors. This is equal to F to the N transpose, which are row vectors of the same length, or maybe isomorphic to this. So that these are row vectors. These things are linear functions. The duals are linear functions. So how can functions equal vectors? Well, they are, but they can basically equal it by isomorphism. So we are so A in Fn transpose or A in Fn or A transpose in Fn transpose, either way. How does this become a functional? Well, we are the dot product. Phi A transpose in V star, sending V in V. I want to make it linear to A transpose V, summation AI VI. So this vector, row or column, V transpose, goes to this linear functional. What is V star? V by V star, I mean Fn star. Okay, so that's the claim. Now, obvious, so let's prove it. Proof meaning that this is really a verification, not a proof. A bunch of bookkeeping. So, proof. Number one is obvious, or it holds more generally. For lin VW. For all W. Not just for W equals the field, but for every W equals. So, of course, it follows that it's a vector space. The second one is where we say, so let's see. So first of all, it's easy to check that this is a linear function. Right? If you take A transpose CV plus W, CV plus V prime, then indeed it is C times A transpose plus V prime. So let's do lots of stuff. So check. This is easy. That phi of A transpose does belong to V star, does belong to Fn star. V belongs to Fn. It's also non V. Certainly, this is easily checked to be a dual. Not only that, so now let's look at the maps, right? So let's give that map a name for all A. Let's put this for all A in Fn. Let's now define this map. Let's give this map a name. So define phi. Do I want to say Fn or Fn star? Phi from Fn transpose, sorry, not star, to Fn star via A transpose. A is a vector in Fn, it's a column vector, A transpose is a row vector, and this is the map that I just wrote upstairs. Define this thing. So clearly now, because we checked that this is indeed a linear map, therefore it is an Fn star, so this indeed lands in Fn star. Okay, define this thing. Now we have to check many things. And we have to check that, well, we just have to check it's a linear isomorphism. So we have to check it's a linear map, it's 1 to 1, it's 1. I think that's all that we have to check. Yeah. And that will be it. Fine. Again, the linear part I won't even bother checking. You guys can check. So check 1, phi is linear. Part 2, phi is 1 to 1. So suppose phi of some A transpose is phi A transpose is the zero map. Right? So the zero map in the dual space. What does that mean? What does a zero map do? Well, the zero map sends everything to A transpose. So, right? So implies what? It implies that 0 of V equals 0 equals phi A transpose of V equals A transpose for all V. That's what it means for a map to be 0. It takes any vector to 0. But the map was supposed to be this guy was 0 because this is in the kernel. So this value must be 0. So this is equal to 0. How can A transpose V be 0? Well, so say that A is equal to A1 into AN. And cleverly choose the vectors V. And V equals EI. Then 0, the scalar 0 equals A transpose EI equals AI for all I. That's what the previous line says. Put V equals EI, you get that the ith coordinate of A must be 0. But if every coordinate of A is 0, then A itself is a 0 vector, and therefore the only map that goes to 0 is the 0 vector. Okay, so it implies A is 0, the 0 vector in F to the N. But that's what did we just prove? We just proved that if phi takes a vector to 0, then that vector is 0. I could even say 0 transpose. So the kernel of phi is 0 transpose. So phi is 1 to 1. Right? Remember, we first check phi is linear. Now for a linear map, if the kernel is 0, then the map is 1 to 1. And finally on to so let's start with, so what do we have to show? We have to show that any linear functional in Fn star is of the form phi of A transpose, meaning it's the transpose against it's the dot product against some A. So let's start with the linear functional. Say phi is in Fn star. How are we going to get, so if you want to say that the phi is precisely the inner product against something, how are we going to get that something? Well, we just take evaluate using exactly the same coordinate basis. Let AI equals phi of the EI Now phi is a vector, phi is a transformation taking column vectors to scalars. So this is a scalar. And A is of course A1 into AN. The claim is that phi is exactly this phi. Which is of course the image of A transpose. And that would prove that every vector, every dual functional phi is in the image of this capital phi, so it's onto. If we can prove the claim, then we are done. Well, why? Because, well, how do you show that two functions? This is, what are these? Remember, this is true in Fn star. Fn star is the set of all linear functions from Fn to the field. So how do you show that two functions are equal on a set? They have to agree at every point. So let's calculate these vectors at every point and see what happens. The claim is this will finish the proof, and let me prove the claim. And can I prove it over there? I might be able to, so let me try. Proof. Let's start with phi of, let's start with this side. So if for V belongs to V, let's say phi of A transpose of V, this is literally just A transpose V, right? But this is equal to summation AI VI. No, even better. Fine, let's just write this down. I goes from 1 to n. And now I, on the other hand, I want phi. Phi of V. Now I know what to do. So what is this? This is I equals 1 to n. What was AI? AI was phi of Vi. So let me not. Let me say this, but except for the fact, these are everything is scalar here. Right? So let me say Vi times AI. In fact, I'll say it here. Why should I wait for that? Right? The inner product of A and V is the same as the inner product of V and A. And so this is equal to this. And now what was AI? AI was phi of EI. That was the definition of AI. But phi is linear. Phi is given to be a linear function. So this guy is exactly the same as phi of summation Vi AI. Right? These are vectors. This is a linear combination of those vectors. Phi of a linear combination is the linear combination of the phi's. So this guy, if you expand it out, it is summation Vi phi of EI. Just exactly what I wrote here. But now what is summation Vi EI? What was V itself? V exactly was V1, V2, Vn. So what is summation Vi EI? It is exactly V. And so we have started from phi of A transpose of V and equal it to phi of V for all V. If two functions, even if two linear functions agree at all points, then they are the same function, and that's what we are saying. So it was 1 to 1, it is on 2, and we are done. Okay, great. That is done. So in particular, what we saw is that the dual space to the row, to the column vectors is the set of row, is the space of row vectors. Okay, great. And so in particular, I can now say the same thing about matrices. Okay, great. I want to get at least to here. Let's see. Let's see how far we get. Fine. Session drinks. Okay, after this, I will do examples of dual more examples of dual spaces. We saw one example here. So corollary is exactly that instead of writing a very long set of column vectors, let me stack them up side by side and make matrices. We've already seen this point of view. This was very nice. So we will, yeah. So for integers n comma n bigger equals 1, the dual space to f to the n cross n star is, well, you can write it in many different ways, but one way to write it is this, is isomorphic to f to the n cross m. The question is really, what is the dual isomorphism, like this isomorphism, right? How do you do this thing? So if you look at the matrix here, right? I will keep the same notation, phi subscript v transpose, where v transpose, the phi v transpose does what? Is supposed to be what? So this is supposed to again be exactly equal to summation bij aij or aij bij. Where I'll say it here. Where phi v transpose of A. So this so B transpose, so B is n by n by n, so B transpose is n by n. A is of course n by n. This is summation aij, bij, I goes from 1 to m, j goes from 1 to n, whatever. You get the idea. I'll just say ij. I'll say ij equals 1 and m comma n. So I goes to m and j goes to n. Okay, and then, but what was this? This is precisely the trace of A transpose B or B. Let's say B transpose A. It's B transpose in A. So we just say. So the trace form is exactly useful again in showing, talking about dual spaces. Okay. I won't even prove this. This is pretty standard from the proposition, or just like it. So now more examples of duals. So we already saw these row column duals and these duals. V star, just duals. Okay, so I'll just say 1, 2, 3, 4. So V star or elements of V star. So we already saw the one example of a dual element, the zero functional. The zero functional takes any vector to 0, that is clearly a linear map. Okay. Now here are other maps. So one is that if you look at V equals f to the n cross n. This is the set of square matrices. Here is a linear map from it, the trace. Okay, the trace is indeed a linear function and a non-zero linear function. Another nice one is V is consider V to be the set of all functions from D to F, or the free D or whatever. Right? With finitely many actually functions from D to arbitrary functions. This is a vector space. Consider evaluation at evaluation. And here at some scalar A. How does this evaluation map work? It's obvious. F goes to F at A. This is a linear function. More examples. Yes. Here are some nice examples. Yes, of course. Just giving the linear maps, right? So yeah. Second. third one is, as I said earlier, the zero functional. This is a linear functional. It is in fact the zero element of the vector space. And then here are two over the real line. F is R. V is the set of all differentiable functions. F from let's say -1, 1 to R, and the map is literally the map phi sending F. This is the element of the vector space of functions to F prime at 0. I claim this is a linear function. Why? Because again, you can just take a look. Right? So phi of CF plus G is the derivative of CF plus G at 0, but that's the sum rule of differentiation or whatever. And where there is differential calculus, of course, there is integral calculus. F equals R. V equals the set of continuous functions. Let's say on 0, 1, on closed 0, 1 this time. And you can guess what the phi is. Phi of F is just the area under the curve, F of t dt. If V is that, then the integral, you can even integrate against a specific function, like f of t times sine t dt. That's a different linear function. One for every different function against which you integrate. Okay, so these are some examples of linear functions. We are still, today we will continue to do linear functions. Today we are not finishing with that. Okay, what next? Now the next one is just a simple theorem or a proposition. So whether we construct a new thing like the sum or the whatever, the direct product, the direct sum, the tensor product, we look also at finite dimensional vector spaces and talk about the dimension of the construction, dimension of the tensor product, dimension of the direct sum. So we should talk about the dimension of a dual space as well. And that's pretty much clear. From all these examples, you can see the dimensions theorem. If V is a finite dimensional vector space, if dimension, let's say over f of V is less than infinity, then the dimension of V star does equal the dimension of V. So you don't lose or gain anything, the dimension stays the same. And that is going to lead us to an interesting property called the dual basis. Okay. Okay, we have time. We have plenty of time. Yeah. And then I actually want to define the transpose. So we'll talk about the dual basis and then we will talk about the transpose of a linear map. For example, the transpose of a matrix. So we are getting there. Fine. So, proof. So let's fix a basis of the dimension is finite, so we can fix a basis of V. That's in fact ordered basis. Say V1, Vn is an ordered basis. Okay, of V. Then I can talk about an isomorphism, right? We know the isomorphism between, so in fact, well, I will jump that step and say I claim the map, let's still call it phi, capital Phi, from Fn star, sorry, Fn star is Fn transpose to V star. I can even call it transpose, doesn't matter. Given by sending A transpose to an element of V star. Let's call it, I'll still call it phi A transpose, sending, let's say, an element V. No, this time I need to say summation Cj Vj, summation Vj Vj, J goes from 1 to n, So this phi A transpose literally just says instead of EJs let me write VJs, but do the same thing to summation BJ AJ. The map phi, capital Phi, sending a vector, a row vector, transposed row vector, to this linear transformation, to this claim, to this function, is indeed a linear isomorphism. And this proof is exactly the same as the proof that the row vectors are the dual of the column vectors. You verify something goes to the right place, then it's linear, then it's one-to-one, then it's on-to. So I won't actually prove this. I will leave it to you to prove. I will simply mention that is a let's finish it. And as I said, I will leave it to you guys to check. It's basically the same proof as that Fn transpose equals Fn star. Okay? But now what happens? Once this happens, then if there is a linear isomorphism, the dimension of this guy is the same as the dimension of this guy. But that is just the same as the row vectors or column vectors, that doesn't matter. This is simply which is the dimension of V. The point is it's the dimension of V. Therefore, we are done. Okay, fine. 1 second, I need to write this. Great. So now, once we have this thing, once we have the fact that the dimensions are the same, you can of course ask, suppose I'm given the ordered basis of V. I know that the dimension of the dual space is the same. Is there a nice ordered basis of V star that sort of fits very well? As examples, maybe I'll write down the question. One second. Yeah, so given V equals finite dimensional vector space with ordered basis, I should need not even have said that, with ordered basis V1, Vn, is there a nice or a compatible basis? Of V star. So, and for example, the basis E1 and E2 and En, and correspondingly the basis of rows E1 transpose, En transpose. And the answer is yes, and this is called a dual basis. So let me first define it, and then I will claim and prove that it is indeed a basis. So definition. So given an ordered basis, so given an ordered basis of a vector space B, of an F vector space B, V, sorry, define the dual basis to be how should I call it, phi V, yeah, phi V1, phi V2, phi Vn. Of course, this belongs to V star to the n. I'll tell you what is phi Vi. So let's say phi Vj naught of, okay, so I need to define this as a linear function, right? Where phi Vj naught of summation bj vj. So take any, this is the basis. So that means every vector is written as a linear combination. Phi of something, some vi or bj naught, is precisely that coefficient, bj naught. That you can easily check this is linear, so I won't even say that. Or maybe I'll say that in the proof. I won't prove it, I'll just say it. Claim one, this is lemma or a theorem or proposition. Homework. It's a homework problem. Very nice. The dual basis is indeed a basis. And I've just told you this is a collection, an ordered collection of functionals. I've not even told you they are functionals, but that's not how to check. This is the claim is it is a basis. That's a homework problem. Another homework problem. This is interesting. Suppose I give you a bunch of non-zero vector spaces, okay? Any collection, I'm not saying this is a finite collection now. Then I've told you about products, I've told you about coproducts, the direct sums, I've told you about duals. I'm going to combine all of them in one statement. Take the direct sum. Take the dual of that. This is the direct product of the individual dual spaces. So when the set I is finite, then both sides are finite and you just say the summation vi star, direct sum vi star is direct sum of vi star. But when it's infinite, then there are interesting. Then you have to have direct product. Not direct sum here is not big enough. Direct product, it's bigger. So that's another homework problem. Great, so that is that. Okay, so now as I said, so I have some time. I'll just do the following. I will define the transpose and we will stop after that. I won't define the perp space. The perp space we will leave for next time. Perp space and double dual will leave for next time. But yeah, I'll define the transpose. Okay, so today's job was to, basically today's class was very simple. Transpose of linear transformation, linear maps. Today we started off by stating and proving the universal property for tensor products. Then that was the end of the category theory section, and then we said let's look at the duals. Look at the duals, basic properties, dual basis, dimension. Now we talk about transpose, and the transpose has to do with duals. The correct way to talk about transposes is because of that example I told you, the example 2 or corollary. It was that the dual space to n cross n matrices is n cross m matrices, and that is how the transpose comes in. Okay, so so proposition. So the first proposition is in the favor of these product and direct sums basically. So I don't know why, but it's just I don't know why this has to do with anything. But maybe this is not your transpose. I'll just tell you a different result. So these two results I'm asking you guys to verify, and the following result I will tell you basically is trivial or something. So another proposition. Maybe I should have called it a lemma. Anyway, suppose again this thing, so say Vi and Wi are F vector spaces for all I in I. So as usual, it's a possibly infinite collection of vector spaces. Then, and suppose I have maps. And Ti belongs to lin Vi to Wi. Then the property of the product, nice property about products is that you can combine all these maps and get a map for all I. then the map T equals, take all the products I in I, lies in both lin the product Vi to the product Wi, as well as the direct sum. I don't even check this. You can, I mean, this is the claim is that these maps are linear, and I'm stopping checking linearity. Ti is linear in both cases and well defined. So I won't check, linearity and well definedness. I've stopped checking. Okay, so that is just some extra proposition. But now comes the transpose proposition. Yeah, I think this is the proposition. Yeah, and that will be the end of the class. Okay. The proposition, transpose. Some people call it the adjoint as well as the transpose, but anyway, it's the same thing. Well, in this context, it's the same thing. So again, suppose we have two vector spaces, say V and W over F are linear, and T is a linear map. Then there exists a unique T star that satisfies, well, it's unique because of the definition. It goes the other way. It goes from W star to V star. So basically, for example, if V is n-dimensional, W is m-dimensional, then you have the space of m cross n matrices here. So this is an m cross n matrix. Then there exists an n cross m matrix going from Rm to Rn, row vectors to row vectors or whatever, such that something happens. Sending. What it sends? It sends phi in W star to phi composed P in V star. Okay. There's not much to do here. I mean, where God is so. So in other words, you define T star. T star takes as input a functional phi, and this is giving you phi composed T, which sends V to what? Phi of T of V, right? So first T of V belongs to W, and phi is in W star, so this takes it to a scalar. And the proof is literally very simple. The proof is, I mean, there exists a map, but of course, and the point is this is linear. Sorry, I should have said it's linear. Where do I say it's linear? Linear T star, linear map T star from the code. So I'm defining T star for you. This is the definition of T star. That's fine. So there is a map that sends it because that's the definition of the map itself. The claim is that this map is linear. Or maybe, okay, maybe the correct way to say it is the map, this thing, sending this to this is linear. And the definition, before I prove the theorem, which is 5 lines or 2 lines, let me just mention that this particular linear map, as it's called, is called the transpose or the adjoint. T star is called the adjoint or the transpose of T. I might be even able to finish on this board itself, but let's see. So proof. I mean, I just said that I'll stop proving things are linear. But fine, one more time for the transpose map. So let's check. So T star of, T star of, first of all, is it in C? Okay, so you have to first of all check that the T star is indeed landing in W star. Is T star of phi in V star? Certainly, T star of phi is a function that takes a vector to a scalar, but is it a linear function? So this is literally two. I'm verifying linearity twice. Yes, T star phi of CV plus V prime. Yeah, so I'm not even specifying that this is a scalar, these are vectors in V. That's obvious. So this is phi of T of CV plus V prime by definition. Here. But now T and phi are both linear maps. So phi composed T is a linear map. So this is of course C times phi of T of V plus phi of T of V prime. This is literally, I mean, it's as bad as just saying I'm changing notation. That's really what it is. But what is this? This is precisely C times, what is phi of T? The C times T star phi of V plus T star phi of V prime. So indeed, yes, it's linear. And V is T star linear. This is the same. T star takes everything to a linear map, but T star itself is linear. Well, T star of C phi plus phi prime. Okay, how do you check that this guy is equal to C T star phi plus T star phi prime? How would you check something like this? These are all functions from V. These are all points in the sum of these guys and that are both points in V star. These are functions on V. To check that two functions of V are equal, you must compare at every single point in V. Let's start with this V and end with at V and at V. Let's check. So this is again obvious, but fine. This is C phi plus phi prime of T of V. But then on the other hand, this is equal to, so now this is linearity in the functional space. The definition of that is equal to C phi of T of V plus phi prime of T of V. And that is exactly equal to that. Phi of T of V is this. So it's literally notation change. It's as bad as that. Okay, but anyway, this map T star is indeed therefore a linear map from W star to V star, and this linear map is called the transpose. Okay. Okay, and that exactly corresponds to the transpose as well. Okay, fine. So that's it for today. That's it for this week, basically. So we will continue with next week with Perl spaces and double duals, and that will end the chapter on dual spaces, I think. Okay, so that's it for now. So I'll just stand back. You can pause the video.